neutrinos than the stuff we're all made of around us in the universe, mostly from the Big Bang, and a lot of neutrinos from the sun as well. And really, neutrinos have always been a little special, even within the standard model, because they only feel weak interactions. So that's both a good thing and a bad thing. The bad thing is that it makes them extremely hard to detect. And that's why progress has been pretty slow, and it has only happened very recently. And just for comparison here, I'm showing for 100 GeV neutrinos, neutrino interaction cross-section of protons versus proton-proton interactions, many, many orders of magnitude difference. So weak interactions are called weak for a reason. And that's pretty much what we knew 10 years ago, that we had probably 3 flavors of neutrinos. And the most important thing is that over the last 10 years, we have had a lot of data. So there is really a lot of progress that has happened. And now we're hoping to make even more progress with neutrinos. So what I'll try to cover is a little bit of a summary of what we've learned over the last 10 years. And not only the science that we've learned from these 10 years, but also the experience and how we've learned from that experience. And how we're going to try to use this experience to probe new environments in particle astrophysics and new particle physics, using the fact that neutrinos feel only weak interactions, and consequently they can really probe energies and densities that we can't access in any other way. And here's just one example of possible sources of both neutrinos and photons, which are out there in the universe. We know all these sources exist. And up here, you get all the electromagnetic spectrum, and down here, it's the same energy range for neutrinos. And one important point to notice here is that at some energy, the universe essentially becomes opaque to gamma rays, while neutrinos can still make it to us because, photons interact electromagnetically, they get absorbed. Neutrinos feeling just a little interactions probably much further. So there is really an unique opportunity here to learn about some astrophysical objects which we can't even access in any other way, except perhaps through gravitational waves, but those are even harder to deal with than neutrinos. So, once again, the most important thing is that this is really an experimentally driven field. And what we thought we knew 10 years ago pretty much turned out to be mostly wrong and turned upside down by actual data. And before I talk about data and how we understand this, since I assume not everyone here really knows how we detect neutrinos, I should explain a little bit. We all know how to detect charged particles. That's easy. There are many ways of doing that. However, neutrinos don't have an electric charge. They're neutrals. They will not leave any track in any detector. How are you going to see them? The only way you can see them is wait for them to interact through their weak interactions, and in that weak interaction produce the charged particle and detect the charged particle. And there are really 2 kinds of processes that you can have that neutrinos can interact through, the so-called charge current and neutral current. In the charge current, the neutrino will make a charged lepton, an electron, a muon, or a tau lepton. And then maybe here kick a nucleus or break off a nucleon or a nucleus or something like that. And here you have this nice lepton that you can try to detect, and a bunch of stuff here. In the neutral current interaction, neutrino will just scatter off a nucleus. So all you can see in an actual detector, the charged particles, are only coming from this kick nucleus or breakup of the nucleus. So it's probably easy to understand for everybody that it's much easier to detect this kind of process than this kind of process, because you have to convince yourself that if you see a bunch of stuff here, it's really coming from a neutrino and not from something else. Also, this process is very useful because we know within the standard model of particle physics, which is very well tested in many kinds of experiments, collider experiments in particular, we know that we always have, in weak interactions, flavor is conserved. So if we had an electron-type neutrino coming in, it will always make an electron and not something else. It will never make a muon. Same way, a muon neutrino will always make a muon, and so on. So if you can measure this charged lepton here, and you can identify which kind it is, you can tell which kind of neutrino it is. So for every single type of experiment, it's important to remember these things, that what we really measure in the experiment are the properties of these charged particles coming out of this initial neutrino interaction. You never see the neutrino directly, you see it indirectly after it has interacted. And you can identify what type of neutrino it is by identifying what kind of lepton it is here. So the solar neutrino problem is one of the oldest problems we had to deal with in neutrino physics. And it's really interesting to remember a little bit of the history, which is that really in the 60s, John Bacall and Ray Davies proposed building a solar neutrino experiment with the only purpose of studying the sun. It was a purely astrophysical motivation for building such detectors, which was to really understand how the sun actually works. Because, well, we kind of knew from Bethesda that the only way it would work is through nuclear fusion, and then it would produce a lot of neutrinos, but it was really this that was driving the experiments was study of the sun. So already in the 70s, we had detected already solar neutrinos. So those were in the Homestake experiment. And from the very beginning, there were a lot fewer than what the solar model predicted. And that's why this was called the solar neutrino problem. However, here, what all these experiments were doing, what Homestake was doing initially, and then later on a bunch of other experiments were doing, was just to count neutrinos, counting new E type of neutrinos. And we know that the sun only produces new E type of neutrinos. Later on, other types of experiments started looking at things like neutrino scattering, where they could really see each neutrino individually and measure its direction and its energy. That added a lot of information to the problem. But still, they were seeing too few of these guys, and the whole community was kind of split. Is it really some particle physics that we're seeing there through neutrino oscillations, or maybe it's the fact that we don't understand the sun well enough? And this debate really went on from the 70s up to pretty much 2000 or something like that. And just to understand that this really was a meaningful question to us, these are just a few of the assumptions that went into the standard solar models. There are nuclear reactions that the solar energies are not measured in the lab. You really have to rely on extrapolations from theoretical models, which have sizable uncertainties. Also, what the experiments were measuring were kind of high energy tail of the data, the so-called boron neutrinos, for which the flux is really very strongly dependent to the central temperature in the sun. It's like really, really high power of the temperature. So you change the temperature by a little bit, you can change the flux by a lot. And then there are also other assumptions about the solar properties and the solar physics which go into these models. So for a long time, people actually said, oh, just astronomers don't know anything and they don't understand the sun. So how are you going to believe that the number that they predict for the neutrino flux? It's probably that. That became harder and harder to accommodate once we got this information about energies and about the energy spectrum, which you couldn't change by changing just these assumptions about the solar model. Most people already believe that it has to do with neutrino oscillations. And in some sense, this is very natural, because everybody expected neutrinos to have some mass. After all, there is no reason why they wouldn't. And once they have a mass, then neutrinos oscillations almost, they're essentially automatic. Because if neutrinos are massive, there's absolutely no reason for the electron neutrino produced in a weak interaction to actually be a mass eigenstate. It's just simple quantum mechanics. It's just the most natural thing to have, that the actual flavor states are just a superposition of mass eigenstates. It's just, you can think of it the way around. You have some massive neutrinos sitting around there. Once they interact, they mix. You start having the new state to be a superposition of mass eigenstates. You have to rediagonalize Hamiltonian to get the propagation state. So that's what happens here. And here I'm speaking to the simplest example where I'm saying, well, let's assume there are just two flavors of neutrinos, even though in nature we know there are three of them. So the whole oscillations, it becomes just solving the Schrodinger equation for the level system. It's just like putting a spin in a magnetic field. It's exactly the same problem. So you just solve the Schrodinger equation to get propagation of these mass eigenstates. You can write it down either with wave functions or with matrices. I always like to write the matrices down because they're easier to generalize when you need more stuff. So again, you can work in either basis, either with these new E, new mu guys, which are the flavor states, which are things which are produced in the weak interaction, or with the new 1 and new 2, which have a definite mass. And if you solve this problem, you can figure out that you get the probability to start out with some flavor state, and after propagating over some distance L, a neutrino with a given energy has some probability to become a different type of flavor. And for this simple two-flavor-like model, it's really an oscillatory term and some amplitude, which is at most 1. And it's important here to remember that all these data that we had for a long time was coming from solar neutrinos, atmospheric neutrinos, were really natural sources where we had absolutely no control over either energy or distance. So L and E here were fixed by nature essentially. And that those sources kind of determined what values of delta m squared we were sensitive to, and by some lucky accident, it happened to be the right values that we could actually measure them over the last 10 years. And the reason I'm saying that once you have L and E determined your sensitivity only to a small range of delta m squared is very easy to understand. If you think of how a sine square function looks like, if this number is really tiny, then you're somewhere here, you're looking at a very, very tiny effect, you're not going to see anything. If that number is very large, on the other hand, the oscillation is so fast that you just can't resolve. All you see is essentially the amplitude. You see the average. You see 1/2 sine squared theta in an actual measurement. So it's really only when this number is of order 1 that you can resolve an actual oscillation. So that was a very easy way to interpret solar neutrino data by using neutrino oscillations. People, however, tried very hard and came up with all sorts of other possibilities, some more complicated, some reasonably simple. And again, you know, from the 70s through the 90s and close to 2000, many people were not convinced neutrino oscillations are really what's going on. What really made a huge difference was the Sudbury Neutrino Observatory's SNO experiment, which was able to measure this harder neutral current interaction. Remember, it was a thing where you only had, you didn't produce a charged electron, so it was much harder to identify. So these guys only did this in 2001. And why did this make such a big difference? It made a huge difference because through this neutral current, you can measure all flavors of neutrinos. All of them, remember, it was just a neutrino coming in and scattering, so it was a neutrino coming out. So any type of neutrino can do that. While the other experiments were counting really just the electron type neutrinos. They were looking at the neutrino coming in and making an electron. So it's only a new E which can make an electron. While here, since you're looking at neutrino and just breaking up the deuterium, you are counting all of them together. And what happened is that they showed that indeed the new E's were missing, but when they were counting all types of flavor together, they were getting exactly what the solar model predicted. So that really showed that it's neutrino oscillations happening. It's really, new E's are too few, but they reappear in the form of Q's and taus. So that was really the definitive proof which convinced everybody. In addition to that, we also got data about at the same time from a reactor anti-neutrino experiment, which essentially sees exactly the same oscillation effect when interpreted in terms of oscillation with exactly the same parameters fitting the data from a man-made beam, or an actual reactor, which has absolutely nothing to do with the sun. So there is no solar flux prediction here. And even here, the solar flux prediction kind of drops out just because you have one flavor versus the other 3 flavors. So the reason I really went through this history and explanation of how we learned about solar neutrinos, and it really took 40 years to solve this problem and to rule out all the other possible solutions to this solar neutrino problem, is that it's kind of useful to remember this lesson when we're talking about future neutrino experiments and how we want to actually deal with those and build them and interpret the data. So it took really 40 years from the first solar neutrino detection, which was motivated purely by understanding the sun, going through all this exercise of finally finding the right observables proofs that we were seeing some particle physics in there through neutrino oscillations, to only now go back to the sun. So now we know enough about neutrinos and neutrino oscillation parameters to actually go back to the solar neutrinos and start fit the data to get things like cross-sections at those solar energies, getting density profile and density fluctuations inside the sun. So we started out with astrophysical motivation, went through a lot of work and a lot of experiments to actually detect some particle physics in there, and now we're going back to learning about the sun, just as we originally wanted. The other piece of data, which really was the first kind of proof of neutrino oscillations, came from atmospheric neutrinos. These are the neutrinos which are produced when cosmic rays interact with nuclei in the atmosphere, and that's pretty much the easiest way to make neutrinos, both in nature, anywhere in nature, and in the lab as well. That's how we know how to make neutrinos. Smash protons into anything, it'll make pions. Pions decay and make neutrinos. So one more piece of information that we have is that when these pions decay, we know the flavor structure of the products. We always get 2 new mu's and 1 new me in a given pion decay. So we expected these neutrinos to be there just because we had measured already the cosmic rays, and you could predict how many you would expect, and also you could predict this ratio of flavors. And what happened is that for a long time, experiments measured this ratio of ratios of predictions to data to predictions to be pretty small. It was really 98 when the big difference was made by Super K, which showed that the number of these new mu's was actually strongly dependent on the zenith angle, on the direction where the neutrinos was coming from, and that's what convinced everybody once again that we were seeing neutrino oscillations, because the guys coming down who had no time to travel were just about what you expected them to be, while the neutrinos which traveled a long distance coming upward were disappearing once again. So just to give you an example of how the data looked like, and this is already a pretty old plot. Now they have even more neutrinos, so it's even better. If you look at electron-like neutrinos, they're kind of what you expect them to be. While if you look at the muon neutrinos, the ones which travel a short distance are just about what you expect them to be, while the guys which travel a long distance are here, are way below what you expect them to be. So those are the guys who have oscillated away. And again, we can interpret this data in terms of oscillations. And now we have a lot of other experiments where we do control energy and distance. They're either reactor or accelerator type of experiments where we see exactly the same effects with exactly the same parameters. So everything fits in very nicely. It's a very consistent picture, verified in many ways. And if you just interpret all this in terms of neutrino oscillations, you end up with pretty much this kind of 2 different mass scales. And this was kind of a lucky accident which allowed us to treat all this data in 2 flavor-like oscillation scenarios, which allowed us to meaningfully make 2-parameter fits to the data instead of 6-parameter fits to the data, as you would have to do if these mass scales turned out to be close to each other. And then something very unexpected, mixing angles turned out to be very large. Maximum mixing for mu to tau neutrinos, pretty large mixing angle for solar neutrinos. And for quarks, we know all the mixing angles are very small, and everybody expected that the same thing would happen for leptons, and it didn't. So this is already telling us something, that we really start learning something by using neutrinos and by measuring these oscillation parameters. Once again, we know that there are 3 flavors of neutrinos. There should really be 3 mixing angles in there. About the 3rd mixing angle, all we know is that it's very tiny. And there is a big effort in trying to determine what this angle really is. So we have 2 very large angles and 1 very small. For this one, we just put on. So that's what we've learned really just over the last 10 years. All the story of neutrino species. Now we're at the stage where, once again, we try to use neutrinos to learn about something else. And that's very useful because really, neutrinos play a very important role everywhere in astrophysics and in cosmology. There are lots of them produced out there in the universe. And because of the fact that they have very high energies and probe very high densities, there are cases where the only way we can learn about some of these astrophysical objects is through neutrinos. So it's very important that they really give us additional information which we can't get in any other way. And in particular, they can test cosmic ray physics, sources of, well, the engines powering with all these astrophysical sources. So there is a lot of potential there. And we definitely know these neutrinos exist. And some models are more speculative, but definitely at some level, while the numbers are very uncertain, we definitely know these neutrinos exist. And the reason I say we definitely know they exist is that we have this GZK process, for example, for which we have detected very high energy cosmic rays. Those we know are there. So this would be these protons. And then we know for sure we've detected this cosmic microwave spectrum. So in the interactions of cosmic rays, high energy cosmic rays with the CMB, once again, smash protons into anything to make pions, you will get neutrinos. The neutral pions give gamma rays, and the charged pions give neutrinos. And once again, the new data in gamma rays, lots of TeV gamma rays out there, that's also suggesting that we should expect a lot of neutrinos as well. Those are likely to come from neutral pi decays, while charged pions will be neutrinos. Numbers here are quite uncertain. The actual normalization of this flux easily varies by a factor of 10, depending on all sorts of model assumptions. But we definitely know these neutrinos are there. We have some idea of the order of magnitude of the fluxes, so we know how to look for them. And that's really the most important thing here, and that's why I'm talking about these neutrinos today, is because we have all these experiments which are now already taking data and building up towards bigger sizes to actually detect these high energy astrophysical neutrinos. So this is really happening right now, and this data should be there now any moment, essentially over the next few years. We should have a lot of these high energy astrophysical neutrinos. We have none right now, but we are just approaching the size, detector size, which is big enough to start detecting these neutrinos. And in particular, there are pretty much 3 techniques which are used. I'll try to briefly go over all 3 of them. One is a very well-tested Cherenkov detection in water or ice in particular here. So the ice cube detector is essentially a big bunch of strings with phototubes in them in ice at the South Pole, covering 1 kilometer per cube of ice. So these guys are just looking for those electrons and muons going, emitting Cherenkov radiation through this, when going through this detector. The other technique, which is sensitive at higher energies, is the radio technique, which again uses ice as the interaction medium. So you're waiting for a neutrino to come in, interrupting the ice, and then when the shower, electromagnetic shower from the electron produced in that interaction here develops, there is coherent radio Cherenkov emission. So what these people do is put some radio antenna on a balloon, which is flying high up over the South Pole, and observe, look for this radio Cherenkov emission. And since it's coherent emission, they have higher sensitivity at higher energies. And they cover 1 kilometer square of ice flying the balloon above the Antarctic. So it's a huge detection surface. And they have flown one of these balloons already, and they should have 2 more flights in the near future. Last balloon flight was a year and a half ago, and they're still analyzing data from that. And I think you already heard the colloquium about that. Half the detector is actually taking data right now, and in a couple of years, they'll have the other half of the detector also installed. The third technique is air shower detection. And in particular, the Pierre Auger Observatory was redesigned to detect cosmic rays. However, it also has the potential to detect neutrinos by looking for horizontal events. Protons would never make it through the whole atmosphere in the horizontal direction, while neutrinos could. So the only problem here is that air is not very dense. So because neutrinos already have very small interactive cross-sections, you don't expect a lot of events here. So in Auger, at best, you can expect a couple of events per year from any kind of flux. So this will be harder, but it can potentially be useful, as I will talk about a little bit later. So okay, the important thing is we know these neutrinos exist, and even more importantly, we have right now the experiments which should be able to detect them very soon. But what are we really looking for, and what do we really hope to learn from all this stuff? Well, what these experiments are looking for are either point sources, really looking for these neutrinos coming from individual directions, and you can do this neutrino astronomy because nothing deflects them, nothing absorbs them, they just come straight to us, which is very nice. But also because most of these sources don't have high enough fluxes and neutrinos are so hard to detect, you often have to really look for diffuse fluxes, essentially from integrating over all sources of the universe of a certain kind. And then you look for these diffuse fluxes, either from this, integrating over all the GRDs or HENs out there in the universe, or from all these cosmic ray interactions with the CMB, which happened out there in the universe, and potentially from either dark matter manipulation or other new physics processes that we haven't detected yet. And once again, this is data which is complementary to the other types of data that we can get through astronomical observations or cosmic ray observations. And often all these observations are correlated. And it's very important to have the global picture of putting everything together and see through consistency checks if what we're measuring makes sense, and we can really learn something out of that. So what we hope to learn is really a lot of particle astrophysics and a lot of particle physics. From the particle astrophysics side, we're really using this fact that neutrinos only interact quickly, so we're trying to push these limits of looking at higher densities, at extreme environments that we can't probe in other ways. And some of these questions can actually be answered just by detecting a couple of neutrinos. If we see 3 neutrinos coming from an AGN, that is definitive proof that hadronic processes are important in AGNs. And that's a big unanswered question in astrophysics. Some people argue that you can get all those X-ray and gamma ray data just by electromagnetic processes, by inverse Hahn scattering or such. Other people argue that you can't do it without having hadronic processes happening in there. This kind of question you can ask just by detecting a couple of neutrinos. From the particle physics point of view, there are 2 things that you're using here to learn something new. One is, again, the fact that they only have weak interactions. So once again, well, actually here, usually it's a high energy which plays for you. Because really, in nature, these things have energies which are way beyond what you can measure in collider. Center of mass energy for these GSK neutrinos can reach 100 TeV or even higher. LHC in the future, biggest collider will have, can't reach even within a factor of 10 of that. So these really are the highest energies that are accessible to us. So it is in principle possible that we will discover something out there just by pushing the energy frontier. At the same time, weak interactions could also help, because even though these are things which are hard to detect, hard to measure, and once you actually have them, they're a lot more sensitive to new physics. Because after all, we know that the new physics is somewhere in the weak interaction range or weaker. If there are new interactions out there, and we believe there are, they're pretty weak. So in the collider experiments, we're trying to look at these small corrections from some very weak process, very suppressed process, to something which has a huge background, usually from stronger electromagnetic interactions. Here, background standard model process is the neutrino process. It's a weak process to start with, so you can have order 1 effects of the new physics. So relative effects can be made. All of them are small and hard to measure, but once you measure them, the effect of new physics on the neutrinos can be of order 1. While in collider experiments, it's weak versus strong, so it's much smaller relative effect. So there's a lot of potential out here. But then we remember the solar neutrino problem. And honestly, it took us 40 years to solve the solar neutrino problems. We knew a lot more about the sun than we know about these astrophysical sources that we're interested in right here. So the lesson there is that we have to be smart about how we learn all these particle astrophysics and particle physics out of any data we get. And this is very important, really. Because indeed, there is a lot of potential, but we also have to remember that there are lots of uncertainties, both on the astrophysics side and on the particle physics side. So it's very important that we actually measure everything we can with the experiments we have, but in addition to that, we really think carefully and we identify from the very beginning, we ask now the questions about what are the relevant observables. What's the equivalent of the charge current versus neutral current measurement in snow, which solves the neutrino problem that we have to think of right now to answer some of these questions that we want answered, such that we separate what's particle physics, what's particle astrophysics, and what the uncertainties are. So, because of this, I'll try from now to walk you through the path of one of these neutrinos, from wherever it's produced until we actually detect it, and to kind of go through the list of things which affect these neutrinos, and the things that we have to take into account when trying to get from whatever we will be able to measure back to what we actually want to learn about these neutrinos and about their sources. So in any of these sources, we kind of know, or want to know, rather, so it's really what characterizes a source is neutrino flavor, the energy distribution. Once you know what kind of process produces neutrinos, these are kind of determined. The one thing is much harder. How many of these neutrinos you really get is kind of not very well known. And you also sometimes need to know where these sources really are, especially if you look at these diffuse fluxes and you try to integrate over the whole universe. Sometimes even cosmology starts playing a role in affecting your results. And once again, the easiest way to make neutrinos is from pi decay. So for a long time, people have talked only about pi decays producing 2 neutrinos of mu flavor, 1 of E flavor. So they talk about this 1 to 2 to 0 flavor ratio. But that's not the full story. That's kind of the most common, simplest thing that you can think of. However, that's far from being always true. There are lots of other processes out there that produce neutrinos. Neutron decay is probably one of the most common ones that only makes new varieties. So it's very easy to actually change this flavor ratio at the source, either by having other processes which produce neutrinos in other kind of flavors, or by having these neutrinos initially produced in pi decay suffer other processes. Like maybe the pion will decay, makes the first mu, but then the muon will be absorbed before decaying again. You don't get the other 2 neutrinos, 1 mu and 1 v. There are all sorts of processes that can happen. Some of them we've studied recently are related to matter effects, which are also relevant in the sun, actually. Once neutrinos go through some amount of matter, neutrino oscillations get affected by this interaction of the matter. It's like, when an electron goes through a plasma, it has an effective mass which is larger. The same happens with neutrinos. Once they go through matter, their effective mass changes such that this oscillation probability is changed. And that change is proportional in some way to the density of the matter they goes in. So that can also affect this flavor of neutrinos. So also together with the flavor dependence, you also get changes in the energy distributions of these neutrinos already at the source. Then you have them getting out of some astrophysical source or other. They have to make it to us usually from very large distances. All these sources are typically very far away. Some of them are really cosmological distances away. So over very long distance, we know for sure neutrino oscillations happen now. And we also know, since the distance is so large, that we'll be in this regime where the oscillation is way too fast to resolve. So all we see is just the air without oscillation. We're only sensitive to these amplitudes. And since, remember, one of these mixing angles was maximal, you have this sine squared theta to be 1. Everybody used to talk about, well, pi decay neutrinos 1 to 2 to 0 flavor composition after oscillations ends up to 1 to 1 to 1 flavor ratio. That means you always get equal numbers of electron mu and tau neutrinos. But as we've already seen, even at the source, sometimes it's not true. You don't start with a 1 to 2 to 0 flavor. And remember also the solar neutrino mixing is also large. So why doesn't that play? And of course it does, and we pointed this out, that solar neutrino mixing also can change the flavor composition over this long distance oscillation. And it's just by accident, actually, that the solar mixing angle comes multiplied by this combination of fluxes. So for pi decay, it happens to be multiplied by 0. But if you have any other flavor composition at the source, if it's not pi decay, which makes the neutrinos in the first place, then the three flavor effects become relevant, and the solar mixing angle also plays a role in neutrino oscillations over this distance. And this stuff, we now know how to take into account, because we have measured all these oscillation parameters in lab experiments. It's just a matter of putting this in. At the same time, there are other things that could happen that we don't even know about. We might learn about them from this kind of data. And usually these are all very tiny effects, which however accumulate over the long distance. So any effect which keeps adding up once you propagate over these very, very large distances will affect, once again, either flavor composition or energy distributions of these neutrinos. Once they reach close to us, they still have to go through the air, through rocks, through ice, to really detect them. And even though these neutrinos interact very weakly, now we're talking about very high energy neutrinos, and the higher the energy, the higher the interaction cross-section becomes. At some point, they will actually start interacting quite big, and you have to take these interactions into account. And of course, all these interactions are determined by interaction cross-sections, which, as we'll see, even within the standard model, we might not understand as well as we would like to understand. And definitely, since we're talking about these very high energies, we might also pick up new physics contributions to these interaction cross-sections. And then once again, we can have all sorts of other things happening during these propagations to matter. And just to show you what the relevant distances are, so now we're talking about neutrino energies 10 to the 6 to 10 to the 12 GeV, giga-electron volt, so 10 to the 9 electron volt. That's pretty high energy. And what I'm showing here is neutrino interaction lengths. So on average, a neutrino of 10 to the 6 GeV will travel about 10 to the 9 centimeter weather equivalent before it interacts. So these are really long distances, but once you reach about 40 dB, the average interaction length will become essentially the diameter of spheres. So above 40 dB, you start getting neutrinos absorbed in spheres. So even neutrinos at some point start interacting. And so the relevant scales here are, kilometers, hundreds of kilometers, or longer for neutrino interaction. And then here I'm also showing the tau decay length, which would be just this, how long the tau will travel before it decays. And again, here we're talking about meters to maybe 50 kilometers. Once you take into account, this also loses a lot of energy. So for people doing accelerator type of physics, they work really, really hard to see tau tracks, which are like millimeter lengths. And here we're talking about 50-kilometer lengths tracks for tau electrons. So it's a very different regime. And in this energy range, neutrino interactions are pretty much the same for all three flavors. However, when we detect them, the three different flavors will look very differently from each other. And that is due exactly to this propagation through matter. And here I'm trying to explain what the difference is. If we have an electron type neutrino, what happens is that it goes for a long distance through the earth. At some point it interacts, it makes an electron. An electron will immediately shower and get absorbed in the earth. So if this electron interacting somewhere here, we'll never know. If it interacts right here inside the detector, we will measure that small electromagnetic cascade or big electromagnetic cascade, depending on how energy it exists. For a muon type neutrino, it can either interact in the detector, but also it can interact somewhere outside the detector. But because the muon track will be now extremely long, it can actually interact somewhat outside and we will still see the muon going through. So now for muon neutrinos, the effective volume for detection is actually larger than real volume of the detector, and it's energy dependent because of course how far a muon travels depends on its energy. For tau neutrinos, it gets even more interesting because for tau neutrinos, as I said before, the relevant distances are between tens of meters and tens of kilometers for the decay length. So what can happen is actually you can have a full succession of events where you have a tau neutrino interacting, producing the tau, and then the tau decays, and that decay produces another neutrino which then interacts again. And you can have a series of these processes happening while this neutrino goes through the earth. So the effective volume for the tau can be way larger. But of course, you can never always win. There is a price to pay for this. And the price you pay is that whatever you see in this detector here, which is the end product of either a neutrino interaction or a tau decay, is much lower in energy than the initial neutrino starting with here. So there is a trade-off between competing effects here, where you gain effective volume, but you lose energy and you risk to drop below the detection threshold by the time you actually reach the detector. So because of this, actually, you can't just quickly get back on the envelope estimation of where you will gain volume for each of these flavors. You really have to go through the full exercise of computing this. So you have to take into account everything that can happen to neutrino. You can either have a neutral current interaction, in which case you still have a neutrino but with a changed energy spectrum in the final state, or you can let the neutrino interact, produce a tau, and then this tau, as it propagates, loses energy through electromagnetic processes. At some point it decays. In the decay it produces another neutrino, and you have to keep following all these processes happening through this propagation. So this is just putting the same thing in aggregation. It's really very simple if you think of it. You start with some flux, some distribution of neutrinos, and then you let them interact proportional to the total interaction cross-section. You lose this flux at a given energy. If it was a neutral current interaction, you haven't really lost the neutrino, you just change its energy spectrum. So you add it back here with the correct energy spectrum given by that neutral current cross-section. If it was a charged current, then indeed you no longer have a neutrino, you've actually produced the charge lepton, produced tau. So you've produced here a tau with a given energy. And tau will travel for a distance, will lose energy in the process, you have to take that into account. Eventually it will decay. Once it decays, you lose the tau, you let it back as a neutrino here, because it's decayed, you have produced the neutrino. You put everything together, you get the result of this propagation, and that's something that we actually did here a few years back when I was here. And here I'm just showing you for a given flux, for this guaranteed flux, which is k neutrinos, for a given trajectory, which is 5 degrees of horizontal. So these are pretty close to horizontal already. Because again, at these energies, very high energy neutrinos get absorbed in the Earth. So if you go through the full Earth, you are left with almost no neutrinos. This is just 5 degrees of horizontal. You start at high energies, they all look pretty much the same. At low energies, the three different flavors look differently because of this propagation effects mostly. Here, the black line is the same thing. It's a tau flux with a proper calculation of everything. And the other curves show kind of simple approximations that people were using before this word, which was either neglecting, for the green thing, they were completely neglecting this change in the energy due to the neutral currents. They're just saying, oh well, that doesn't matter. And it's true, it doesn't matter much at low, but the intermediate energy range, but it does matter at high energy. And even more importantly, people were completely ignoring the tau energy loss through electromagnetic processes. And that turned out to be a really big effect. You were grossly overestimating the tau fluxes by forgetting that those taus actually lose a lot of energy before it came. So this is just kind of supposed to show you that for different directions, if you go through more material, essentially you lose completely high energy part of the spectrum. You have no neutrinos left at high energy, but you can get a lot more effective volume at low energy. As you go through less material, then you keep most of high energy guys, but you no longer get this big enhancement at low energies. And all of this, again, was determined by the neutrino interaction cross-section. And what is typically done in order to compute this neutrino interaction cross-section is that we take cross-section that we can compute, which is based on our present knowledge and present data, and then say, well, we assume that nothing else happens. It turns out to be a power law. And then we assume nothing else will happen for another few orders of magnitude. So it just takes the power law and trivially extrapolate it at higher energies. And that's what all those results were based on. But the question is it a good assumption? Is it true that nothing will happen for another few orders of magnitude? And here, I'm showing you a calculation which is just within QCD. So just standard model processes, where for those who know what I'm talking about, you take into account log x, you resum the log x's. As you go to higher and higher energy, you're probing smaller and smaller values of x. And there are some log 1 over x's in the cross sections that you have to resum. So even within QCD, you can get at very high energies, you can actually get a significant difference in cross sections compared to the trivial extrapolation. Because the point here is that there is an uncertainty in this neutrino interaction cross section, even within the standard model, which can dramatically change predictions for the fluxes at very high energy. And I will get back to this in a little bit. So the message here was really that there are lots of things going on just with what we already know. And of course, the most interesting stuff is the physics beyond the standard models that we're looking for. One important point there is that any new physics will add to the neutrino interaction cross-section. I haven't yet found any model where you get destructive interference between standard model and new physics processes to actually lower the cross-section. Typical thing is that you have the standard model cross-section and you add something. What does this mean? It means that if you're looking at outgoing neutrinos, higher cross-section means more absorption. So you will lose more and more of the volume because essentially the more stuff you go through, the more neutrinos get absorbed, if cross-section is higher. So you're forced to look at events only at almost horizontal or downgoing neutrinos. Of course, people have talked about all sorts of other new physics that you could be sensitive to in this, either in the neutrino, either affecting the neutrinos you detect, or actually directly detecting this new physics in the same type of detector. But the message here is that once again, because of all these problems and all these uncertainties, it's very important to think about smart ways of being sensitive to one thing at a time. And here in particular for cross-sections, actually there is a way to get rid of all these uncertainties, even though we don't know what normalization of the fluxes are. What we can do is to look, for example, at angular distributions. And angular distributions in the data would be a perfect way of determining the neutrino cross-section, because if you have any isotropic flux, the absolute number, as long as it's non-zero and you see something, doesn't really matter. All you care about is to compare neutrinos coming from this direction with neutrinos coming from that direction. And in that case, if the flux is isotropic, the only difference you expect is from the fact that they travel different distances, they go through different amounts of material, so the absorption will be different, and that absorption is proportional to the cross-section. And the good thing is if you can look both at upgoing neutrinos and downgoing neutrinos, you always get something. Because if the cross-section is very high, then you will get a lot of absorption, you lose a lot of the outgoing guys, but the probability for them to interact in the detector gets higher. So you get a much higher probability to get the downgoing guys. If, on the other hand, cross-sections turn out to be smaller, like in some of the QCD cases, then you will have essentially no neutrinos coming down. The probability for those to interact in the air or in small volume of the detector becomes very small, but then you have a lot more of them making it through the airs because you get a lot less absorption inside the airs. So by looking at these angular distributions, you can really be sensitive only to the cross-section and get rid of the other stuff. And again, it's very important to really look at very specific signatures, to really take advantage of this information that you can get through flavor composition, energy measurements, angular measurements. Because as I've said, you always have to deal with competing effects. You always want, you want a small cross-section, not to get too much absorption and lose all your neutrinos on the way. But with a small cross-section, you have also a small probability of actually interacting inside the volume of the detector. Same thing with propagation. You get a much larger effective volume, but you get a lot of energy loss at the same time. So because of all these competing processes, you really have to be careful to go through a full exercise of propagating the neutrinos correctly, taking into account all the effects in all the relevant energy ranges, and try to make a good use of this. So the advantage of the whole thing is we first need to see these neutrinos. These we're pretty confident will happen and will happen extremely soon. But as we've learned already from solar neutrinos and atmospheric neutrinos, counting neutrinos will likely not be enough to answer most of the questions. As I said before, they might be able to answer some questions just by detecting a few neutrinos and just by counting neutrinos. But most of the interesting stuff, both for astrophysics and particle physics, requires a lot more than that. It really requires getting these angular distributions, energy distributions, flavor composition, and every other single thing that you can think of. And that's where most of the work is really going into right now, is putting in all these details, really thinking of new ways and new tricks for identifying either flavors or getting the better measurements of either energy or angular distributions. And of course, you can't make a distribution with 5 neutrinos, so it will take a little while to accumulate a lot of data enough to really measure all the things that we're after, both in particle physics and astrophysics. At the same time, we might get lucky. Transient sources can easily give you a few hundred events, but of course, the probability of having a transient source happen right now is not so large. It's just like for supernovae. We would learn an enormous amount of things about supernovae, including the galactic supernova today. It would be tens of thousands of neutrinos, lots of information, but you only get a few of these per century. So with transients, it's always tricky. With just continuous sources, we will eventually get there, but it won't be this year. However, the important thing is that if we do it the right way and we spend the time right now to optimize the analysis we will do of all this data, what to actually look for, how to do the analysis, will actually make it possible to distinguish between all these possible uncertainties, both from the particle physics side and particle astrophysics side. And by combining all this information, we really can learn something faster than the 40 years it took to sort out the solar neutrinos. And for the last few minutes, I would like to now go back to atmospheric neutrinos for a little bit because atmospheric neutrinos really gave us the first evidence for neutrino oscillations. But now, as always, are becoming the pain for some experiments. They will be background for all these physical sources. IceCube already has thousands of events of these atmospheric neutrinos. They haven't seen an astrophysical neutrino yet, but they have thousands of events already of these atmospheric neutrinos. It's true the flux is dropping with the third power of the energy, so it's dropping pretty fast, but still in the high energy IceCube range, there are lots of these guys. So if you want them or not, they're there. In IceCube itself, the energy of this neutrino is pretty high. However, recently, over the last years, there has been a lot of activity in building a so-called deep core array inside IceCube, which essentially is a bunch of extra strings, a minimum of 6 which are already funded and possibly 10 which might get funded. In addition to the 80 strings that IceCube already has, now the proposal is to put in additional strings which have much, much denser photon coverage. So the reason that they want this is to look for either dark matter manipulation, but mostly for galactic sources. This experiment is a south pole. Galactic center is above the horizon, so they have to look at downgoing neutrinos to see galactic sources. Problem with looking at downgoing neutrinos is that you have to deal with the muon background. There are lots of cosmic muons coming down. Even going deep into the ice, the high energy muons will make it all the way down there. So first of all, they want to put this array in the center of IceCube such that they can actually use IceCube strings around this denser array as veto. And also in the deepest part, because, well, they get fewer muons as they go deeper, and also from their measurements, ice properties are much, much better in the deep ice. And then the main problem with the muons in IceCube was that one of these very high energy muons can come in and go in between the strings, in between the IceCube strings. And they would miss that muon, but they would see the scatter and they would confuse that with the neutrino. With this dense array, since now they would have very high coverage, photon coverage, they wouldn't miss the muons anymore. They would really see the muons coming in. They would reduce their claim is the muon background by 6 orders of magnitude. So that really allows them to look for galactic sources. So this was their main motivation. It was a big deal. And as I said, it's already funded. So this will happen in season 2009-2010 season. They will start putting in the new strings, which much denser photon gives. The other thing that they gain by this very high coverage is energy threshold. And by having all this coverage, that means you can have a lot less energetic muons traveling very short distances and still catch them in these phototubes rather than going in between like in IceCube. So the energy threshold actually goes down to 10 GeV neutrinos. Once you go to 10 GeV neutrinos, well, you have lots of these guys, lots of atmospheric neutrinos that you already know, and now you can measure them down to 10 GeV energies. That's exactly where the neutrino oscillations actually happen. It's between 10 and 40 GeVs that they're important. So going back to this story that, well, we really know that there are 3 flavors of neutrinos, so if you want to look at neutrino oscillations or mixings, there are really these 2 delta squares that we've measured, these 2 mixing angles that we've measured, and then these additional mixing angles that we haven't measured, we just know that it's small. And then there's also some phase about which we know absolutely nothing. And there's really a lot of effort in planning new accelerator experiments and all sorts of other experiments trying to measure this delta 1,3 value, this CP violation phase. And another thing that we don't know is really this, if this delta m squared value here, which is the difference, it's m3 squared minus m2 squared. We don't know if that's positive or negative. We don't really know if m3 squared is smaller or larger than m2 squared. So again, a lot of effort is going into trying to go after these parameters, but the problem is that none of these experiments exist yet, and if they will exist, it will take a very long time for them to get built, get data. Because once once again, they're hard and expensive. So what we came up with was, well, this information is already in these atmospheric neutrinos, because these atmospheric neutrinos do travel long distances, they do travel the full diameter of the Earth. And going through the matter in the years, they oscillate, and the matter effects are sensitive to these values of θ13 and this hierarchy. So we have shown actually through analysis, again using Andrew distribution and energy distributions and the full chi-square fit to this simulation, that it is possible with 5 years of data in this deep core array of ice cube to determine the hierarchy if the θ13 values are not particularly small. So the right edge of the graph is the present limit. So you really do cover significant parameter space in θ13 just by using atmospheric neutrino data. And here, it's kind of the number of neutrinos as a function of energy. Actually, here it's really a number of muons as a function of muon energy, detected muon energy. And if you look at the numbers, it's 6,000 here. So you do get a lot of neutrinos, and this high statistics is what really helps. And the conclusion here would be that even though it's a very hard experiment, and I don't have time to explain, but there are lots of uncertainties, and you really need all this type of information about Andrew distributions, energy distributions, to take full advantage of all of that to actually get to this result. It's probably the only data we will have over the next 5 to 10 years, which is sensitive to this, so it's definitely worth doing. It also helps to better understand the atmospheric neutrino flux, which will be a background for astrophysical sources. So in some sense, it also helps data analysis by better understanding the background.